Alrighty, so this is the Chem 111 in review. It's pretty brief. It should be stuff that you guys have gone over today. Probably finish chapter 4. So I'm going to start with effective nuclear charge. You'll see it in the book and with Mr. Fisher as the Z number. It's really just the number of protons in the nucleus. It also indicates the positive charge of the whole atom. Effective nuclear charge takes electron shielding into account. You'll see Z effective as the terminology for it. Electron shielding is the phenomenon where electrons are attracted to the nucleus but are also repelled by one another. So as they're going around, say this is your nucleus, you have your first, second, you'll have like little atoms kind of going around, but they'll also be repelling each other. So you'll never find them together, you'll never find them like that. They'll always be pretty far apart magnetically. Since they're both negative charges, they don't want to, of course, meet up together. So now chapter 4 goes over periodic table and periodic trends. So here's a brief overview of the periodic table. We'll start with the main group. Now the main group, you have your alkali metals. Alkali metals are all of these here. And you have your alkaline metals, which are all these here. Metalloids are all of these darker green ones, and then your non-metals are all of these. Now, non-metals are exactly what they sound like. You usually find them in gaseous, liquid, or other phases other than really solid metal. You'll, of course, find solid carbon in a lot of places, but you'll usually find it in gaseous form. Transition metals. Now, transition metals are everything in between. It's going to be your D and your F subshells. So everything in the middle, basically, is going to be all of that. And the transition metals. Now, transition metals act a little bit differently than your main group and your noble gases. You'll come to that later in later chapters. The major thing to know about noble gases is that they have full subshells, and as such they do exhibit some weird properties, such as they have basically zero electron affinities, meaning they don't want any electrons, and we'll get to electron affinities a little bit later in these slides, since the subshells are full, so they don't want to kind of unbalance themselves. They're exactly where they want to be. And because the subshells are full, we use them for abbreviations. So like if you have, let's say, neon, and then like 1s2, 2s2, that kind of stuff. And you'll see that as well. And then we get on to our first trend, which is going to be our atomic radii. Now, atomic radius increases from right to left, increases from top to bottom. So, for example, helium should be really small for radius-wise. The major thing to know about radius, especially for atomic radius, so helium has 2 protons, so it's got, you can think of it as a +2 charge in the middle, and then you have 2 electrons. Now then, those 2 electrons are going to be held on to that 2 plus pretty tightly, since it's just the 1s shell. For example, if we were to compare it to hydrogen, for example, so you have 1 plus, and it's only trying to hold on to 1 electron, so it's kind of weaker. So the atomic radius will be bigger, comparing hydrogen to helium. All right. Next one I have here is ionization energy. Ionization energy is pretty big in these next coming chapters. Ionization energy is the minimum amount of energy needed to remove an electron from an atom in the gas phase. Biggest things to note, it's harder to remove a paired electron than an unpaired electron. So for example, if we have beryllium and boron, for example, so just think of this as like your 2s2, and then for beryllium, for example, is just 2s2, right? And then boron, for example, so we could also put our 1s, I guess. We have our 1s right here. So this would be a representation of beryllium, right? It's only up to 4. And since everything's paired, it doesn't want anything, it doesn't want to get rid of anything, it's good to go, basically. But on the other hand, if you were to make boron, this is your 1s, 2s, then you have 1 more. It has an unpaired electron, so it really wants that other electron in here so that it can complete that pair. But however, one thing to note is that with boron, not only would it get, if it got another electron, it would go into the next box, of course, then another one would go to the next one, and then you just start pairing them from there. But it's a lot easier to take off this one lone electron than it is to break a pair of electrons. So that's the basic gist of it. It's also harder to remove an electron with a full or half-full subshell. So, for example, if you had nitrogen versus oxygen, So let's say this one on the left is nitrogen. Nitrogen goes up 1, up 1, up 1. Again, this is your 2p shell. This is your 2s. This will be your 1s. All right, and again, 1s, 2s, and your 2p over here. So this will be, this one over here on the left will be your nitrogen, basically. And then this one on the right, when I'm done filling it in, will be your oxygen. Okay, so if you were to try to ionize nitrogen versus oxygen, it's a lot harder to take one from nitrogen since it has a half-full subshell. Oxygen, on the other hand, is a little bit over, so it's a lot more stable if it has a half-full, or at least more so than if it has this extra one in here. So if oxygen can get rid of that one, it wants to, so it's a lot easier to ionize oxygen than it is to ionize nitrogen. All right, electron affinity goes along with ionization energy, except for it's kind of the opposite. So ionization is how much energy it needs to get rid of an electron. Electron affinity is the energy released when something takes in an electron. So basically how much it really wants that electron is what I think of it as. The higher an electron affinity, the more accepting an element is to an electron. So it's harder to add an electron to a half-full or a full subshell. So for example, if we were to do beryllium and lithium, so like you would have your 1s, your 2s, let's see, lithium. So okay, so we'll have lithium on the left, this will be our lithium, and then we'll have beryllium on the right. Okay, so again, this is going to be your 1s, and then you're going to have your 2s. Okay, so for lithium's sake, it only has 3 electrons, right? And then beryllium has all 4. Now then, basically, the gist of this is that lithium wants that extra electron more so than beryllium. So lithium, I always thought of it as it's kind of hungry, right? It's missing one. It wants to fill in that slot and get that extra electron so it can fill its 2s subshell. Beryllium, on the other hand, is already full. So for it to take in an extra electron, it would take, it really doesn't want that extra electron. So this is half full. You could technically say this is a half full subshell, but this one is full, like completely full. Well, it's harder to add an electron to the full one than it is to add to the half full one. All right, so then I have some periodic trends here. Now, the cool thing about ionization energy and electron affinity is that they both increase from left to right, with some exceptions. One exception in particular to remember is nitrogen. Nitrogen doesn't want an electron. It does not want to give up an electron. It's one of the weird ones. We looked at phosphorus, for example, which is right below it. It could really use an extra electron. It's more accepting to an extra electron, but nitrogen does not want one. It does not want to give up one. That's one of the main exceptions to it. Otherwise, both ionization energy and electron affinity increase from left to right. Now then, metallic character is another one that's good to memorize. Metallic character increases from right to left and top to bottom. Now, a good way to remember this is that the further away it is from the noble gases, the more metallic it is in nature. So like the noble gases, of course, are gaseous in nature. So the further away you can get, the better. Now, if you look right next to it, you have your nonmetals, right? And then next to those, you have your metalloids, which exhibit characteristics of both nonmetals and metals. And then the further left you get, if you look at francium, I believe is what it's called, in the bottom left here, it's of the alkali metal group, basically. So it's very metallic, very, very metallic. With just these trends taken into account, it's the most metallic element. So basically anything on this side is going to be very metallic. And then, of course, down towards the bottom is going to be even more metallic. So that's really all you need to know for metallic character. Just remember, nonmetals, metalloids, noble gases, those don't really exhibit metallic character except for the metalloids. Everything else is strictly metallic in nature. All right, so now isoelectronics. That's going to be, I don't know why it's so blurry. So isoelectronics are some of the most confusing things in this chapter. You probably have questions with it on your homework and stuff like that. Isoelectronic basically means that they share the same amount of electrons, but they're different proton numbers. So for example, I have some here. So of course you have the ion, so the nitrogen ions, which are 3-, so it means it gained 3 electrons to move up towards neon, basically. So these have the same amount of electrons as neon, but you have different protons. So for example, if we were to go and draw this out just real quick, so that's 7+. So then you have your 1s, and then you have 2 electrons floating around that. You have your 2s, you have 2 electrons floating around that. And then you'd have your 2p, and then you'd have that full with 8, or 6 technically, right? So 1, 2, 3, 4, 5, 6, and 7 and 8. Now then, that's a really quick and brief overview of that. Now then, if you were to, for example, increase the positive charge, so instead of a 7+, let's say it's a fluorine ion, so it's a 9+ instead. So let's change our 7 to a 9. Everything would move in closer. So if you think about it, if you have like a really small magnet and a really big magnet, which one's going to attract more? The bigger one. That's the gist of it. And basically, in this analogy, your nitrogen's the smaller magnet, and your fluorine's the bigger magnet. Now then, you'll notice that I put some other ones in here, like aluminum and magnesium, right? So magnesium, for example, since it's 2+, I listed them all out right here. So in order, it would go from largest to smallest. Your nitrogen's going to be the biggest because it doesn't hold on to those electrons as well. So of course the opposite is true of what I said before. Instead of holding on tighter, it holds on looser, and it gets bigger and bigger. So nitrogen doesn't hold on that well. Fluorine holds on better, but not as well as your magnesium, and then your aluminum holds on even more. So your aluminum, of course, has 13 protons in it. So you can see that although they all have 10 electrons, they're all isoelectronic. Aluminum, since it has the biggest positive charge, will hold on the tightest, basically. All right, so that's all I really have for your Chapter 4 review. A couple other things to note. So you kind of need to know your nuclear charges and whatnot. Now, nuclear charge is just the protons. So just look at the number of protons, and you'll be golden.